The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
The final quiz is scheduled for a week from today, on December 8th. Following that weekend, we'll have one class on the 13th, and the last days of class are Monday, Tuesday, and Wednesday, the 12th, 13th, and 14th. So I know a number of you spoke up last time and said that you have a conflict on Thursday, the 8th, with a quiz in another class. So could I see a show of hands again of how many of you have this conflict? So 3, 6 people, 7 people. You're going to enroll in the other course just so you can put off taking the quiz. Okay, so all right. Well, that's unfortunate. I don't think anybody should have to take 2 quizzes in one day. We can't move it up. We'll have to move it back. So I don't know if I'm violating any institute rule, but I know that it is strictly illegal to give assignments that are due after the last day of classes, let alone have a quiz after the last day of classes, which has not been previously scheduled as a final examination. So we can't give it after Wednesday the 14th, the last day of classes. So do any of the 6 impacted people have a strong preference for when we should schedule the quiz? Do it Monday? It doesn't have to be that soon. Monday?
Why not Tuesday?
Because Tuesday we have a class.
Well, we would have a Thursday class instead, correct?
No. If we're doing Monday, if we're doing it after the quiz next week, there's a class. We have a last meeting here on the 13th. Yes, I'm not going to shift it for other people, just for the impacted. Okay. Okay. So of the 6 who are entitled to vote, how many would prefer to have it Monday? How many? Monday, the 12th? 3, and I know how it's going to turn out. And for Wednesday, the 14th? 3.
I can't take the test not because I have another test, because I'm out of town, and I'm not coming back till Saturday, and
okay.
Monday's just a little quick to take it after this back.
Okay. I think I'm going to have to make an yes.
Professor, when you mean by conflict, do you mean having an exam at the exact same time?
No, it's on the exact same day, which I think is, considering this is a 2-hour examination, to have another examination exactly the same day. You know, if you're not brain dead after an hour or 2, you'll be pretty close to it. So I think that is an unfair penalty to pay. Okay, I think to keep it as close as possible to the quiz that the rest of the people will be taking, why don't we make it, since it's a tie vote on Monday the 12th, do it sooner rather than later. And I'll let you know next time of where we will hold it. I'll have to arrange a room for it. Okay? So that will not be a make-up quiz. It would be a made-up, invented quiz. Okay, very good. And as I say, on Monday I should have all of the homework and the previous quiz to return to you. The reason you don't have it now is all the little crabbed handwriting that you see before you in the form of these notes, which takes forever. All right, so since we've satisfied the unpleasant aspects of the end of the term, let's get back to discussing some of the other piezoelectric effects that we have defined, and then also ask the question rhetorically, is there anything like a representation surface for a 3rd rank tensor property? And it doesn't look promising, but there are some things that we can do to discuss variation of properties with direction, and we'll see directly what those are. But first, let's look at the converse piezoelectric effect. And this, again, is a 3rd rank tensor property, But what we do is to have the elements of strain, epsilon ij, a second-rank tensor, and to take advantage of this curious relation between the direct and converse effects, we define the converse piezoelectric effect as giving you 9 elements of strain in terms of a third-rank tensor dijk times E sub I. So what is not standard is our convention for the order of the subscripts on the moduli. And hey, we make up the rules. We can do it any way we like. And the advantage of defining it this way in non-standard tensor notation is that we can use the same coefficients for both the direct and the converse effects. So let me, to illustrate what these equations look like, write out a few examples. Epsilon 1 would be d1jk times E sub 1. I'm writing it in simple fashion, not expanding fully just to save space and time. Epsilon 2 would be d 2jk times E2. Epsilon 3 will be d 3jk times epsilon 3. And let me stop after these 6 terms and write, at least for these, an expansion, because this gives us some interesting information. What am I doing that equal signs in here? So this would say that the element of strain epsilon 1 is d1 times E1 plus D112 times E2 plus D113 times E3. And I want to say this is 11K, and I want to say that this is 22K. Yeah, erase that. Okay, the next term would be epsilon 2, and that would be D122 times epsilon 2 plus D 212. Yeah, you're right. This should be this epsilon jk equals d I jk times E sub I. Yeah, so this is all E1. This is E1. And this 1 goes with this one. This 2 goes with this one. You're right. E2. And this is the 311 times E11. This would be 122 times E1 plus 222 times E2 plus D2, D322 times E3. And the fourth one would be E33 equals D133 times E1 plus D233 times E2 plus D333 times E3. Okay, these elements here are the 3 that appear in the box that I had indicated for the terms d I djk. Okay, when we write the direct piezoelectric effect, this would be the box of coefficients. When we write the converse effect, this is the box of coefficients. And now what I wanted to point out is that delta V over V is equal to epsilon 1 plus epsilon 2 plus epsilon 3, which is the trace of the strain tensor. And we're going to get one set of terms which depends on the x1 component of the field, another set of 3 terms that depend on the x2 component of the field, and another one on the x3 component. If these if these expressions sum to 0, then there would be no volume change. So this first set of three of the first 6 equations give you an indication of when the application of a field will result in no volume change in the sample. And that, again, I remind you, can be for two reasons. It could be because all of these 6 of the 9 piezoelectric moduli are 0, or alternatively, if you examine the form of the piezoelectric moduli matrices that is required by symmetry constraints, you'll find that there are a substantial number of point groups for which some terms are 0, but then there is in addition an equality between some of the other terms which make the volume change 0, even though not all of the elements within this half box of moduli are 0. So that is an interesting effect. And it turns out that the majority of the non-centrosymmetric point groups do not have a volume change when you apply in a field in any way you choose. A few do, but it's a minority. All right, but this is not the main point of writing this. I wanted to pose it at this point and then point out that this tells you something about the volume change. And then we would have additional terms. We would have a term of the form E1 something like E1, 2, 3, or E1, 3, 2. And this would be E1, 4. This would also be E1, 4, since we replace both of those subscripts by a single subscript. And the tensor elements that would go in here would be D1, 2, 3. We just want one of them, D1, 2, 3, times E1. And then we want D2, 2, 3 times E2. And then a D3, 2, 3 times, D3, 2, 3 times E3. Okay, we're writing one of the specific equations for the shear strains. If we write the expression for D132, this is going to be D132 times E1 plus D232 times E2 plus D332 times E3. Okay, there are two interesting consequences of this. The strain tensor is symmetric. And this element of strain, well, I've got 3 subscripts in here. Don't want that one in there. Okay, these two strains are equal, and therefore, if we would apply just an E1, for example, let E be equal to just a component of field along X1. The strains have to be equal, but we have 2 different tensor elements here. And the only way that strain can be symmetric, and it's defined as such, is that D123 be identical to D132. And that resolves the issue that came up in connection with the direct piezoelectric effect. We said the direct piezoelectric effect depends just on the sum of the elements dij, and dikj, and since they're lumped together, all we can measure is the sum, and so we'll just have to call that a single matrix element. The converse piezoelectric effect tells us these tensor elements have to be equal if the strain tensor is to be symmetric. So that says that since we defined D16 as the sum of D123 plus D132, this says that D132 is equal to D123 is equal to 1/2 of D16. Just making the equality in the reverse direction. The converse effect lets us say that 123 has to be 132, and any ijk has to be equal to a jk. So if I tried now to write this first expression in the reduced subscript notation, E23 is what we let E5 be. And now we have this equal to, in our reduced subscripts, we have this as 1/2 of D16. And the field that's multiplying this piezoelectric modulus is E1. And that messy factor of 2 has come back to haunt us again. It's like trying to stuff a jack-in-a-box back in the box that keeps popping up. We ate the factor of 2 in defining the matrix representations of the piezoelectric modulus. And now when we try to go to a reduced subscript notation for the converse piezoelectric effect, we've got a 1/2 in there. And similarly, the second equation would be E5, same result, epsilon 5, and it's 132, but 132 is 1/2 of D16 times E1. And we have similar mess for the other coefficients here. So what do? Do we say that the relation between strain, epsilon j, I, epsilon j equals d I j e sub j, has a 1/2 in front of some of the coefficients and not in others? Well, we can't really absorb the factor of 2 in the definition of the piezoelectric moduli because we've already done that. So the only thing we can do is to say that we will have to take the off-diagonal strains and define them as having a 1/2 in front. And when we add these up, we will have get rid of this factor of 2. So we will have to write matrix strain in this reduced subscript notation. We'll have to take E11, epsilon 12, epsilon 13, epsilon 21, epsilon 22, epsilon 23, epsilon 31, epsilon 32, and epsilon 33. And in converting this to matrix form, we'll call this epsilon 1, analogous to what we did for the tensile stresses. Call this epsilon 2, and this epsilon 3. And then for all of the off-diagonal elements of strain, in order to avoid the factor of 2 popping up in front of the matrix representation of the piezoelectric moduli, we're going to have to put in here 1/2 of epsilon 4, 1/2 of epsilon 5, and 1/2 of epsilon 6. And same for the off-diagonal terms, 1/2 of epsilon 5, 1/2 of epsilon 4, and 1/2 of epsilon 6. So the moral of this story is that you can't win, but if you play it right, you can come out even. So only if we define the reduced subscript strains in this fashion can we write an expression of this form. So this algebra is carried through for you for the other elements in the notes, but this is the way we are forced, unless we want to have a factor of 2 in some terms and not in others, is the way we have to define matrix strain. All right, all this is formalism and definition. But I'd like to now do 2 things. First of all, give you some examples of real numbers for piezoelectric moduli, and then ask the question about representation surfaces. Once again, these numbers are in the handout for you, so you don't have to make note of them. But one of the very important piezoelectric materials is the quartz form of SiO2. SiO2 has many polymorphic forms. Quartz is the form that's stable at room temperature, and it has point group 3,2, asymmetric, and there are higher temperature polymorphs of SiO2. There's a phase transition in quartz to a more symmetric form, and then there are cubic forms at the highest temperatures. Now, quartz is not the material that displays the largest piezoelectric moduli, but it has the following advantages. One is it is a naturally occurring material that is very inexpensive, so it's not an exotic, expensive material. Very stable, it's not water soluble. Extremely tough. You can take a thin wafer of quartz, for example, if you want to make a monochromator for a diffraction experiment. You can take a thin wafer of quartz, bend it like this, and it does not break. Very elastic. And if you want a material that's going to earn its living by being squished, you want something that doesn't plastically deform and something that is very hard and resistant to stress. So quartz, even though the moduli are not the largest, is a very attractive material and is used in a variety of devices. There was a time when CB radios were very, very popular, and everybody had to have one in their car, I guess so they could pretend that they were truck drivers. But anyway, you don't have them anymore now that cell phones have come in existence. But for your CB radio, you needed something called a crystal. And they were fairly expensive, and the number of channels on which you could communicate depended on the number of crystals that you could plug into your CB radio. The so-called crystal was exactly that. It was a little black box that looked almost like a transistor, and there were two leads coming out of it. If you ever got curious and broke this thing open, what you found was a nice wafer of quartz, and on the wafer of quartz, brazed onto it, were two wires, and that's all there was in the box. The crystal really was a crystal, and the crystals had been very precisely ground to thicknesses such that when a field caused these wafers to hit a resonance, that resonance would be at exactly a particular frequency, and that was the frequency of that channel. One of the crises during the Second World War is that the highest quality natural crystals of quartz come from Brazil, and during the conflict, the sea channels were essentially blocked, and so people, in order to make all these communication devices, had to learn how to synthesize crystals of quartz synthetically. And there are a number of companies such as Sylvania up on the North Shore that developed entire buildings devoted to growing single crystals of quartz. And they're big tanks, like something out of the aquarium. And in the center of the tank is a rod, and seeds of quartz are placed on the rod, and the thing very slowly rotates around in this solution. And on the rod eventually are single crystals of quartz that are this size. And it's a very spectacular thing to see. In any case, symmetry 3,2, and the moduli that are 0 and non-zero, if we refer the reference axes to a set of coordinates with x1 in this direction and x2, since it has to be orthogonal to x1, in between the twofold axes, and x3 up. And for all materials of commerce that are anisotropic, there has to be some standard for defining the choice of axes. For example, crystallographers would say the unique axis should be along the z direction, the x3 direction, but why isn't x1 and x2 in between the twofold axis? There's some professional society that is responsible for giving standards for representing property measurements in some mutually agreed upon form. And this is the standard set of axes for Quartz and Symmetry 3.2. The moduli, dij, not dijk, but dij, these two are constrained to be equal. This one is 0. This is minus 0.67, 0, 0, 0, 0, 0, 0, 0.67, 4.6, 0, 0, 0, 0, 0, 0. One of the strange materials for which no field can create a strain. A field along X3 cannot create a strain. And these are all in units of 10 to the minus 12 coulombs per Newton. An example I give you here, if you apply a field of 100 volts per centimeter, which is not terribly large, but would be comparable to what you have in some electronic device, perhaps. So this, since our units are MKS, this would correspond to 10 to the 4 volts per meter. The strain epsilon 1, which is D11 times E1, turns out to be minus 2.3, which means it contracts. That's the significance of the negative times 10 to the 4. And that turns out to be 10 to the minus 12 times 10 to the 4. That turns out to be a strain of minus 2.3 times 10 to the minus 8th. 10 to the minus 8th is not exactly a large strain. You're not going to see the crystal wafer twitch and jump if you apply a field of 100 volts on it. But yet, even a strain of this sort is more than enough to be useful. But this is just to illustrate that quartz is not the most sensitive of piezoelectric materials. Another one that I give you data for is so-called ADP, and this is a widely used material. This is ammonium dihydrogen phosphate. And this is one of a family of salts that have very large piezoelectric responses. The nice part about it is that it's water soluble, so you can grow very, very large crystals easily from solution. The nasty part about it is that it is water soluble, so you have to be careful to protect this material from moisture if you're going to use it in any sort of device. But if we look at the moduli relative to the standard axes, and this has point group 4 bar to M, so X3 is taken along the 4 bar axis. Then there are twofold axes and orientations like this. And since they are orthogonal, you can take both X1 and X2 along the twofold axes. And the numbers here for Dij are 0, 0, 0, 1.7, 0, 0, 0, 0, 0, 0, 1.7, 0. This is one of the interesting tensors where there's a diagonal row of non-zero terms off on the right-hand side. And finally, the big surprise is the third modulus is 51.7. So you can see this has a very strong effect. This is over 10 times the maximum piezoelectric modulus in quartz. So this is a material that's very commonly used in transistors and transducers. This is again times 10 to the minus 12 coulombs per Newton. One of the very, very exciting developments in recent years is a class of materials that are Parov Skites. And they are very, very new. The I'll give you the reference to the first one that was reported, and that was just in the spring of 2000. And these are Parov Skites. Parov Skites are materials that in the type form are cubic, but depending on composition and temperature, they can transform to a distorted version of this very simple cubic structure that is tetragonal. And this material can exhibit piezoelectric effects, and whether it distorts or not depends on the relative sizes of what goes into the Parov Skite. Parov Skite has a composition AbO3, like barium titanate is one example. And the material has two different cations, and they have different valences, so they have different sizes. And I won't bother to describe the structure, but it is only a very restricted locus in the field RA versus RB, where both the A and the B can remain in contact with the oxygen without distortion, and it turns out to be a line that does something like that. Any other Parov Skite, and there are lots of them in this field of radii, has to have one of the ions sort of flopping around, and if that gets too serious, the structure distorts so that all these ions can remain in contact with the oxygen. Okay, in order to do that, many of them distort to tetragonal forms, others distort to superstructures which have very, very large unit cells. But in any case, there are, when you're right at the phase boundary between the distorted structure and the true Parov Skite structure, these materials sometimes have very, very complicated X solutions of the two phases on a very fine scale. And it's not known exactly why they have this property, but they have absolutely enormous piezoelectric moduli very close to this phase boundary. And the reference that I give you here is a compound that is a lead titanium zinc niobate. And the complicated composition is to get you close to this phase boundary. This has a D33 that is greater than 2,000 picocuries per Newton. And pico is 10 to the minus 12. So this is a piezoelectric modulus that is 10 to the 3 times D11 for quartz. So 3 orders of magnitude stronger than this very commonly used piezoelectric material. Some of these materials have strains getting close to 1%. So this is something that will actually twitch on the lab bench when you apply a field to it. So these are entirely new. People still don't know the origin of this behavior, and it's still under considerable study. So this is a new family of materials that's very exciting and undergoing a lot of investigation and development work at the moment. All right, we are almost out of time. Time goes fast when you're having fun. Let me raise the question that we'll consider next time, which will be one of our last lectures, and that is it possible to create representation surfaces that tell you how the piezoelectric properties of a particular material will vary with direction? Well, vary with what? Well, if we talk about the direct piezoelectric effect, this gives us components of, well, let's look at the simpler one in terms of what we apply. We have the converse piezoelectric effect that says that epsilon ijk is going to be dijk times E sub I. Okay, so we've got a piece of material, and we apply a field, E sub I. So we can vary this in space relative to a coordinate system x1, x2, x3. But how in the world are we going to show what happens? So I always do an extra thing in here. Okay. There are 9 components to the strain tensor, which is symmetric, so there are really 6 responses that are unique. So yes, we can define the direction of the applied field, but there are going to be 6 different strains. So we're going to need 6 representation surfaces, one for each of the 3 tensile strains and one for each of the 3 shear strains. So you can't do it with a single surface. So you can't do much other than say there are certain responses which are intended to emphasize one particular sort of strain or one particular sort of polarization. So one of the things we might do is to cut a very thin plate of something like quartz and subject it to a uniaxial stress. Okay, so let's say sigma along the x3 axis. So we're looking at a very restricted strain tensor. That's 0, 0, 0, 0, 0, 0, 0, 0, sigma 3. And in response to that strain, there are going to be 3 different components of the polarization. Polarization is manifested as a charge per unit area. So if we make a very thin plate, to be sure, there will be charges induced on these thin edges. But if it's got an area, a surface area that's large compared to the area of these thin edges, we are going to be measuring primarily P3, the component of polarization that's normal to the surface, and that might have a charge per unit area that is comparable to these other 2 charged surfaces. But because the area by design of our specimen is so large, the response that would be most easy to detect and which would be the largest response by design would be P3, which is the charge per unit area on this surface. Okay? So this is an effect we can define for a particular sample and for a particular special form of the generalized force. And we then can ask, what is the value of the single modulus that relates P3 to sigma 3? And that's a question we can ask. And we can plot that response as a function of direction of a plate that we consider as being cut out of a single crystal in different orientations, and then ask how this modulus which connects the 2 changes with the orientation of x3. So that is a question we can ask. And these surfaces are absolutely wild, highly anisotropic, can be identically 0 in certain special directions, and they are very interesting and a lot of fun to look at. So we'll take a quick look at a couple of those, which won't come as a surprise because they're already worked out for you in the notes. So we'll take a look at one of those, and in the problem set, I invite you to amuse yourself by looking at such representation surfaces for 2 other point groups. And with that, having kept you till 5 after the hour, I will quit.